Welcome back, everyone. In this video, we're going to learn about ebook chapter 1, lesson 7, and specifically we're going to learn about spectroscopy. So after reading this section in the ebook and after watching this video, you should be able to describe what happens to light when it's transmitted, emitted, or absorbed and reflected. You should also be able to use the color wheel to identify complementary colors and be able to analyze a simple absorption spectrum. You should also be able to talk about what happens, generally speaking, as light is absorbed. What happens on the molecular level to the chemicals involved. So let's talk first about what is spectroscopy and why you should care. So spectroscopy is the study of how light and matter interact. And a whole lot of what we know about the molecular structure and atomic structure of the world, of the universe, comes from spectroscopic data. We've used spectroscopy to study galaxy for many years, study the galaxy for many years. We use it to identify what elements are in the sun and other information about the whole universe. We will talk about in Chem 110 about how spectroscopy is used to study the greenhouse effect and changes in our Earth's climate. Spectroscopy is also used in water quality studies to examine the acidity and analysis of various minerals that are within water samples. Spectroscopy is also used in pharmaceutical development, and it can be used to examine and track specific molecules for medical studies. So really, whether you're interested in physics or whether you're interested in the environment or whether you're interested in medicine, there's an application of spectroscopy for you. And so I would encourage you to do some of your own digging and figure out what applications of spectroscopy are in a field of your interest, so then you can have a better appreciation for this amazingly powerful field of study. So light can interact with matter in a variety of different ways. I mentioned briefly about emission. This is where you have a light source that is giving off its own light. What happens here is the material, as it gives off light, or it goes from high energy to low energy. So this occurs when you have a light bulb. If you have fluorescent lights looking up at the ceiling, you look at neon lights that are on the street corner, etc. These are all examples of emission. These are all sources of light. Once that light has been emitted, it can be absorbed. So let's say you take a light bulb and you shine light from the light bulb and it goes through a solution. That solution appears green. Some of that light is being absorbed. However, some of that light is also being reflected or scattered. And for colored materials, they will absorb light that corresponds to the chemical nature of whatever's in that solution. And the rest of it gets reflected. So we have light from a source, let's say a light bulb. It goes through and it hits I've got green colored hand sanitizer here. And so some of the light is getting absorbed by the chemicals here in my hand sanitizer, and some of it's getting reflected. You could also have, let's see here, I've got a green screen. And in this case, most of the green light that is on the green screen is getting reflected by that green fabric. We call the light the distribution of light, the wavelengths that are involved of a given emission or absorption, a spectrum. We call that a spectrum. And so the instrument that's used to measure the spectrum of a sample is called a spectrometer. So what we would have is a light source that gives off light. It goes through a prism or a grating, and what that does is that splits that light into its components of its various wavelengths, and then it reaches the detector. If you're in Chem 111 this semester, then you will get to do an experiment where you look at the spectra of various light sources. And you could actually, when you're in person, if you take Chem 111, you'll get to make your own spectroscope. It's actually quite simple and can be done for just a couple bucks. And then you can go around and look at various light sources and see the spectra that they give off. And what we can see is that there are continuous spectra, and then there are more discrete spectra that give off very particular wavelengths of light. And so these are all going to be a function of the chemical nature of those spectra. The chemicals involved will determine the type of spectrum that you get. And what we see here is that the energy of that light is proportional to the wavelength, or excuse me, inversely proportional to the wavelength, directly proportional to the frequency, as we saw in earlier videos. And so by looking at a given spectrum, you can determine the energy of light that's involved there. So let's take another look at an example here. So going back to a green object, if you have a green glow stick, then again, that is dealing with emission. If you have a green colored solution, like my green colored hand sanitizer, then what's happening there is that it is absorbing certain wavelengths of light. Whereas if you take a look at my green cloth from my green screen, it's reflecting, it's scattering certain wavelengths of light. Now, how do you tell what type of, or what wavelengths of light are being emitted, absorbed, or reflected? That's what you're going to need to determine. So, when it comes to emission, what you see is directly proportional to the emitted light. So when you see green light, that's because from a light source, that's because the light source is emitting that green light. And so in this case, we're looking at the wavelength of about 520, 550 nanometers. For absorption, which is the case of the green solution on the screen, the green solution here, the light that is absorbed is not green, but it is the leftover light. So what we see in the case of absorption is what is not being absorbed. So what color then would be absorbed here? Mostly things that are not green. And generally speaking, you could simplify it by looking at the complementary color on the color wheel. And we'll look at that in just a moment. So the color wheel, which you should know from Basic Art 101, helps us to understand what we perceive. So when we see, move my face, when we see an illuminated light, the white light is given as, if something gives off white light, then what we see left over is what is unabsorbed. And so if we look at the complement of a given light, then that's going to be the color across from it on the color wheel. So red is the complement of green, orange is the complement of blue, yellow is the complement of purple. And so if you're given a particular wavelength or a particular color, you should be able to give an approximate wavelength or an approximate color that is complementary to that. So if we give you an absorption spectrum, let's predict what color it would appear. So if we're given an absorption spectrum, remember that what is absorbed is the complement of what we see. And so in this case, we see that it's absorbing in the red range here. And so it would appear to be somewhere in the green range. And it's important to note that complementarity is a property of light. or excuse me, it's not a property of light, but it's a property of our vision. It's how our eyes interpret things. And so if you were to use a spectrometer, then it would need to be calibrated differently. But for us, for what we see, when we see a solution that appears green, that's because it's absorbing, for the most part, red light. When you see an opaque object, like a green sheet, that's because it is reflecting green light and mostly absorbing its complement of red light. All right, so let's do a comprehension check. Let's see if you can figure this out on your own. There we go. Get that out of the way. So, below is the spectrum of a laser dye, coumarin 334. What colored solution, which of the solutions that are labeled there, A, B, or C, would contain this dye? Go ahead and pause the video and try this on your own. Okay, welcome back. So how would you determine this? Well, you've got an absorption spectrum here, and we can see that it has some peaks here in about the 200 range, and then a very, very large peak here around 450 nanometers. So because we have an absorption around 450 nanometers, and this is a colored solution, we know that the color it should appear would be its complement of what it absorbs. Since it absorbs in the blue region, we would expect it to show up somewhere in the orange color range for its observed color, which would give us then an answer choice of A. Okay, the last thing that we're going to talk about is how does light interact with matter? What does it actually do to it? So a lot of that depends on the energy that that light contains. So what we see here is a division based upon the regions of the electromagnetic spectrum. And generally speaking, the higher the energy, let's look at this in terms of wavelength. First, we have it going from low wavelength to high wavelength. We know that the frequency is the inverse of that, and we also know that energy is inverse of wavelength. So our highest energy rays are gamma rays. Because they're so high energy, these can break apart chemical bonds. These can ionize atoms. These can do a lot of destruction. X-rays can also do a lot of destruction, which is why when you go and you get an X-ray, the X-ray technician goes behind on the other side of the room. They make you wear a protective lead covering, so that way only the part of your body that needs the X-ray is getting introduced to those X-rays. As we go down lower in energy, we see that ultraviolet light, it can also ionize atoms and break chemical bonds, although it won't be as strong. UV light can also promote electrons to higher energy transitions. So this is where, if we, in the case of ultraviolet and visible light, what we might see is a substance that absorbs that light and then it re-emits it. And we'll talk more about that once we start looking at chapter 2. Visible light can also do the same thing. It can promote electrons to higher energy. We can get electronic transitions. Infrared light, we sometimes refer to this as heat. This allows us to increase the kinetic energy of our substances, as well as microwaves. Those increase the kinetic energy by inducing molecular rotations. Radio waves, those end up dealing with flipping the nuclear spin, and we're not going to talk a lot about that in Chem 110. Some of the most important ones you want to realize are that these high energy radiation, UV and above, those can generally break chemical bonds. Our mid-range, these can cause electronic transitions. And those are the two main types of processes that you want to be aware of. We can have chemical bond breaking, and we can have electronic transitions. Okay, that's it for this video. Thanks for watching. Have a great day.